So, in the previous lecture what we saw is that instead of using fixed length code, if you use variable length code and you know the probability model of the source, that means you know with what probability a particular symbol comes out. In that case, you can use a better mechanism, you can exploit this knowledge and you can encode the source in such a way that you reduce the number of bits required to effectively encode the source. And with the particular example that we discussed, we showed that instead of 2 bits that are required for a fixed length code, you can effectively use on an average 1.5 bits to encode this source. Now, if we move ahead with this particular example, and what we had chosen is a code which is in this form. Now, instead of this, if suppose we would have chosen a code which is C of A is equal to, let us say 0 and C of B is equal to 1 and C code, this is the code map of C is equal to 1 0. What is the problem or what is the advantage? What we do by designing a code in this manner is that previously you can see that we had one code with 1 bit and 2 codes with 2 bits. Now, we have a better situation. This has a length of 1, this is a length of 1, this is a length of 2. So, if you are going to calculate the average number of bits that is required, what you get going by the example that we calculated, 1 multiplied by half plus 1 multiplied by half plus 2 multiplied by 1 by 4. So, that would lead to a half, sorry, 1 multiplied by 1 by 4, this is the probability of occurrence of B. So, that is half plus 1 by 4 plus 1 by half. So, that means 1 and 1/4 or 1.25 bits. So, this particular method of encoding that we have done over here reduces this to 1.5 bits. Okay. But if I look at the stream of bits coming in at the decoder, if I have sent A, B and C, in this case I would get a 0, a 1 and a 1 0. The receiver, or let us say I get a few further sequences and so on, would not know whether this means a B or whether the receiver should read these together to mark it as a C, right. So, that means these codes have a problem of ambiguity, whereas if we take this particular code the way we have marked it and we want to send ABC, the sequence that would come is 0 followed by B which is 1 0 and we have C which is 1 1. Now, the receiver can use a method saying that I will read the code, I will immediately go and look up. Of course, for all this point initial synchronization is assumed. So, initial sync is always assumed. It will go into the lookup table and it will find that 0 is a code word. If 0 is a code word, it will immediately decode this to a C, to a A. Next it gets a 1, it goes to the code book, it finds there is no code word with 1. So, it waits, it reads the next code book, next incoming bit. It goes to the code book, it finds there is an entry of 1 0. Through this entry of 1 0, it maps it to B and it decodes it to B, right. Next it finds a 1, it goes to the code book, it sees there is no entry called 1, it comes back, it reads the next entry which is 1, it goes back, it finds 1 1, it decodes it as C, right. Now, you could say do the same thing for the previous code and it would work. Let us see, a 0, it goes to the code book, it reads it at A, no problem. Then it finds a 1, it goes there, reads it as B, no problem. Then it finds a 1, it goes there, reads it at B again. Now, this is wrong because the transmitter has sent a 10 for C. So, that means this particular code word cannot be decoded immediately. So, therefore, we can say that there is a decodability issue with this particular code, and this brings us to the motivation, or this gives us the need for defining something known as unique decodability. So, at this point, if we try to recall the fixed length code words, so for fixed length code words, you would remember that we said we require 2 to the power of L, which is equal to, or M should be less than or equal to 2 to the power of L. This is the particular criteria that we had set for fixed length code, whereby we said that L is the minimum integer for which this condition is satisfied. So, such that each of the symbols is assigned a unique code word, otherwise we need not have used that particular expression, right. So, we already have defined that in case of fixed length codes, that we are choosing the number of bits required to represent a symbol, so that each symbol gets a unique code word. So, for a fixed length code, it is almost designed into the system that each symbol will be unique. So, whenever I get a sequence of bits, the receiver knows that it is a 3-bit sequence, or it is a 5-bit sequence, or it is a 7-bit sequence, that means depending on the value of the L. So, the receiver would know the value of L. So, it will wait for so many bits, go to the lookup table and read it off. It is very simple. So, suppose we have 00 to indicate A, 01 to indicate B, 10 to indicate C, and 11 to indicate D. So, if there is a string of this coming, it will know that it has to read 2 at a time. So, it is going to read this, go there, it is a B. Again it will read this, go there, it is a B. It will read this 10, it is a C, 11, it is a D, again 11, it is a D, 00, it is an A, 01, it is a B. So, there is no confusion about decoding. So, fixed length has no problem, but whenever you are designing a variable length code, it is very important that we bring in this notion of unique decodability into the picture, right. It is an important property for variable length codes. This is very important. What it means, we can write down that it means that for any sequence of source symbols, that sequence can be reconstructed unambiguously from the encoded bit sequence. Of course, we would assume initial synchronization. So, that is definitely assumed. So, what we are trying to say is that it requires code for a j not equal to code for a I when I is not equal to j, right. So, this is a clear requirement that the two codes do not match. There is a primary requirement, and that is obviously met in case of a fixed length code. In case of variable length code, in one case we have said yes, it is true, and there is also another very important property which we are coming to, that is known as prefix free condition. So, that would definitely mean that any code word cannot be a prefix of another code word. So, that means in this particular example that we have taken here, what we have seen is here we are going to define all these things, that here 0 is not a prefix of any other code word, 1 0 is definitely not, 1 1 is definitely not. But if we look at this particular set of code words, what we find that this 1 is a prefix of this code word. So, that means code word for B is a prefix for code word of C, and that had caused all this confusion. So, with this we move forward and we would define these things further. So, for unique decodability, we would say that a code C, let us say we define it as C, for a discrete source is uniquely decodable if for any string of source symbols say x1, x2 up to xn, the concatenation of the corresponding code words C of x1, C of x2 up to C of xn differs from the concatenation of the code words of C of x1 prime, C of x2 prime, C of xn prime. By prime we mean a different choice of symbols of any other string x1 prime, x2 prime up to xn prime of source symbols. So, that means in that case we would say that C is a uniquely decodable code. Now, this is by definition of a uniquely decodable code. So, with these two definitions, this is an explanation that we have given, and this is the definition that we have given for a uniquely decodable code. We are going to use this in further designing variable length codes. So, not only this, as we just mentioned about the prefix free condition, which we have explained over here, that here this is a prefix of another code word. So, we need to now go into the definition of prefix free code. So, by a prefix free code, we have to first define a prefix. So, we will say a prefix of a string y1, y2 up to y of L is any initial substring y1 up to yl up to yl prime, where L prime is less than or equal to L of that string. So, what we mean is that suppose I have 0, 1, 1 is a code. So, there are 3. So, 0 is a prefix, 0, 1 is a prefix. So, prefix free code should not, if it has this as a code word, should not have 0 as a code word, and it should not have 0, 1 as a code word, because these are prefix. And we further go on, the prefix is proper if L prime is less than L, and then we say a code is prefix free if no code word is a prefix, that is what we just said, of any other code word, right. So, if we take the earlier example that we had given, that means we have already taken a prefix condition. Now, if we take this example that we had used, here what we find 0 is not a prefix of these two, and there is no code word which is 1. Now, suppose I had chosen, suppose in this example, so instead if I choose C of A is equal to 1, C of B is equal to 1 0, code of C is equal to 1 1. Clearly, it violates the prefix free condition, because 1 is a code which is a prefix over here, right. So, this is not a prefix free code, whereas this particular example, C of A is equal to 0, C of B is equal to 1 and code of C equals to 1 1, this is a prefix free code, all right. So, this is how we can distinguish between a prefix free and a non prefix free code, right. So, we can move on further, and we would like to clarify that given a prefix free code, C, a corresponding, this is important, let us define it first and then we will explain, a corresponding binary code tree can be defined. This is very interesting, which grows, so we are defining it first, which grows from a root on the left to leaves on the right, representing code words. Further, we say that each branch is labeled 0 or 1 and each node represents the binary string corresponding to the branch label from the root to the node. So, if we read this, given a prefix free code C, a corresponding binary code tree can be defined which grows from a root on the left to leaves on the right, and these leaves they form the code words. So, there will be code words and these are nodes. So, each node or each branch, first we say each branch is labeled a 1 or a 0, each branch is labeled a 1 or a 0, all right, and each node represents the code string from the root. So, if this is a node, so you can grow it further. So, if this is a node, this node would represent the code which is 1 1 and the code at this point would be 1 1 1, the code at this point would be 1 1 0, the code at this point is 1 0, code at this point is 0 1, code at this point is 0 0 and so on and so forth. So, you can form a binary tree and you could use this in designing prefix free codes, as we are going to see shortly. I would further say that the tree is extended just enough to include each code word, that is, nodes in the tree are either code words or proper prefix of a code word. Now, what does it mean is that tree is not arbitrarily designed. That means, you can say that I start off a binary tree from here from the root it grows towards the right, and then I keep on doing like this. So, that means this is 0, this is 1, this is 1, this is 0, 1 0, 1 0. So, this would mean that the code word here it is 1 1, code word here it is 1 0 1, here it is 1 0 0 1, it is not ending, it is here 1 0 0 1, 1 0 0 1 and a 0, and here it is 0. This is well, this is fine, but it says that the tree is extended just enough to include each code word in the node in the tree are, that is to include each code word, that is the nodes in the tree can either be code words or proper prefix of a code word, nothing else. So, in this case what we find is that this tree is extended beyond the need, it has gone beyond the need, and there is unnecessary extension over here, which will be clear when we discuss about the other things. So, another particular example that we can take is we have 1 and 0, we have 1 and 0, and this goes there. So, we could label from our example this as the symbol A, this with the symbol B, and this with the symbol C. So, B has the code word of, in this case, 1 1, C has the code word 1 0 1 1 0 1, this has the code word A is equal to 0. So, in this fashion if we design a code book, then we can find that none of the codes are prefix of any other code. Even if we take this, the code word is 0, 0 is not a prefix, 0 is not there in any other code, 1 1 is not present as a prefix, there is no 1 1 sequence over here, even 1 0 1 is not a prefix over here. So, if you are going to design codes in this fashion, then you can make variable length codes which are not prefix of any other code. But however, there are certain more conditions on this binary code tree which we are going to see, so that we do not have an unnecessarily large code word, and that would be able to help us in minimizing the number of bits that we provide on an average to each symbol in a probabilistic manner, so that we reduce the average number of bits required to represent a source symbol through variable length coding. So, we are going to stop this particular lecture at this point, and we will move further in the next lecture, trying to see how one can calculate the minimum number of bits required to represent a code word for a given particular source. Thank you.